So we've said that the generation of light within a laser is not a thermal process. It comes about by stimulated emission. So we need to now think about, well, what does that actually mean to stimulate the emission of radiation? Let's go back to our two-level atom. So we've got energy level 1, energy level 2. The number of atoms in level 1 is N1. Number of atoms in level 2 is N2. And so the energy gap is just the difference between these two energies. And we're going to say that there are only two energy levels, so that if we add together N1 and N2, we get the total number of atoms within that assembly. So we've already seen that we can have light coming in, and if the energy that light carries is equal to the energy gap, then an atom can be promoted, or it can make the transition from level 1 up into level 2. Now, once it gets up there, it's going to stay there for a while. But any system, if you give any system too much energy, it usually likes to get rid of it. So if you heat something up, eventually it cools down. If you have a pencil balancing on its point, then it's got too much potential energy, and what it wants to do is to fall over and lie flat. So giving it that extra amount of energy, moving it up into energy level 2, eventually what will happen is it will relax back down, and if the transition is allowed, then it will relax back down into level 1, because there's nowhere else for it to go, and it will give out a photon again. The next process is what happens if we already have an atom which has a value for E2. It's already in energy level 2, and a photon comes by. Okay. What we've got here is spontaneous absorption. What we have in the second case here is spontaneous emission, so it just happens in a random process. But if this photon is travelling by this particular atom, which is sitting at E2, what can happen is it can stimulate the transition. In other words, it can force the atom down into energy level 1, and you've got your original photon, but you've also got another photon now. And that's how we get light amplification. We started with one photon, we end up with two photons. And so this process is referred to as stimulated emission. The Einstein coefficients tell us something about how easy or how quickly it is that atoms can move between, or make the transitions between energy level 1 and energy level 2. So just dealing with a simple two-level system, the energy levels are infinitely sharp and non-degenerate. So in other words, G1 is equal to G2, so we don't have to worry about degeneracy. The total number of atoms is fixed, and we are allowed to make radiative transfers between those two energy levels. In other words, we can absorb a photon and we can emit a photon. Any atom sitting with energy level 2 can emit a photon or lose energy by emitting a single photon and ends up in level 1. Or an atom which is sitting in level 1 can absorb a photon and end up in level 2. And the condition for that to happen, as we've already seen, is that the energy gap between these two energy levels must be equal to the energy of that photon. So there are three processes here. There's absorption, there's spontaneous emission, and there's stimulated emission. So we'll think about each of these in turn. For absorption, we have our two-level energy system, and we have N1 atoms sitting with that amount of energy in our box, and N2 atoms sitting with E2 energy level in our box. If we have the light passing through and it gets absorbed, we have a transition going from level 1 up into level 2. So we've decreased the number of atoms in level 1, and we've increased the number of atoms in level 2. So how quickly does that process happen? What's the rate of change of the number of atoms in level 1? Well, it depends on how much light we put in here. So if we put in lots of photons, then we can get lots and lots and lots of atoms making that transition. So it depends on the energy that we put in, the radiation density, but it also depends on the number of atoms in level 1. If N1 equals 0, in other words, we have all of the atoms sitting up in energy level 2, then if the photon comes in, there are no atoms down in energy level 1 to actually do any absorbing. So the rate of change of the number of atoms in level 1 is proportional to the number of photons which come in, and also the number of atoms we start off with. And that constant of proportionality is referred to as the Einstein coefficient. And we have a minus sign here because we're reducing the number of atoms in level 1. Okay. The way of thinking about this is that the Einstein coefficient times the energy density, the radiation density, is equivalent to the probability per unit frequency that a transition will occur. Okay. You can use a statistical approach to this. Let's not complicate it any further than we need to. They're proportional, and it depends on how much light you put in and the number of atoms that you start off with in level 1. And we have a constant of proportionality. Let's think about the spontaneous emission. So again, we have energy level 2 and energy level 1. And we have an atom which starts off with E2 joules, whatever E2 happens to be. Now, we've said that this is a spontaneous process, so basically we have to just wait for a while, and then eventually the atom will go down from level 2 into level 1, and it will give out some light. So in that process, we've decreased the number of atoms in level 2, and we've increased the number of atoms in level 1. So again, we can think about what is the rate of change of the number of atoms in level 2. So dN2 by dt will depend on how many atoms we've got up here. Does it depend on any incoming light? No, because it's a spontaneous process. So it only is proportional to the number of atoms that we start off with in level 2. And again, we have a constant proportionality, and this one is now called the Einstein coefficient. And we have again a negative sign here because we're decreasing the number of atoms in level 2 with time. Notice that n is just a number, n2 is just a number here, and d by dt is obviously a rate of change, and so our Einstein coefficient must have units of per second. Spontaneous emission, generally we don't characterise it by talking about the A coefficient, the Einstein A coefficient. We talk about the lifetime. In other words, we talk about, well, how long will the atom in general stay with that amount of energy before it falls down here? And there will be variations in it. And again, there will be some which stay a long time, some which stay a short time, but there will an average across that distribution of lifetimes. There will be an average, and that average we will denote as tau, and we'll call it tau to 1 because we're going from level 2 to level 1. And the value for tau is just 1 over the Einstein coefficient. Okay. So we can think of the lifetime as being how long will the atom stay in that excited state. So maybe a few milliseconds, maybe microseconds, maybe nanoseconds. Stimulated emission. So again, what we have is energy level 2, energy level 1. Number of atoms is N1 in level 1, N2 in level 2. And now we start off with an atom in level 2, and we have a photon passing by that atom, and if it's close enough to the atom, and we'll come back to what we mean by if it's close enough a bit later, but if it's close enough to that atom to interact with it, then it can force the transition from level 2 into level 1, and we end up with 2 photons. Okay. So we've stimulated that process, we've stimulated the emission of another photon. In other words, we've stimulated the emission of radiation, and that produces gain. We've got 1 photon going in, and we've got 2 photons coming out. Okay. Again, let's think about how does that change with time? What's the rate of change? If we have lots of light going in, so we've got lots of atoms up here in level 2, if we've got lots of light going in, then we will get more stimulated transitions. So it depends again on how much energy we put in. Again, it depends on the number of atoms in level 2. If we have no atoms in level 2, if they're all sitting down in level 1, then we can't get any stimulated emission. So it depends on N2. And again, we have a constant of proportionality, which is our Einstein coefficient, or B Einstein coefficient, but this time with the subscript 2, 1, because we're going from level 2 down into level 1. And again, we have a minus sign here because we have a reduction in the number of atoms in level 2 over time. Our emitted radiation, therefore, has 2 bits to it. It has a spontaneous part, and the intensity is proportional to the Einstein coefficient, and its phase is independent of any external field, any radiation field. We don't need to put light in to make that happen. And we have stimulated emission, and the intensity of that is dependent on how much light we put in, the number of atoms that we have in there, and so on. Now, the key thing that makes laser light special is that if we have stimulated emission, so we have a transition, we have 1 photon coming in and 2 photons going out, there is no way that we can tell which was the original photon. They are completely and perfectly identical to one another. They have the same phase, the same frequency, the same polarization, the same direction. Everything about them is identical. They are indistinguishable from the stimulating photon. So the stimulated emission is very different from the thermal emission that we saw when we heated up bits of metal and so on. There, the frequencies will be all over the place, the amplitudes will be different, the phases will be different, the polarizations will be random. Laser light is very special because it is coherent, because these 2 photons are completely and utterly indistinguishable one from the other. So let's put all 3 processes together. If we've got the atoms that are moving up from level 1 to level 2 because of absorption, we've got atoms moving down from level 2 to level 1 because of spontaneous emission, and level 2 to level 1 because of stimulated emission. So the number of atoms in level 1 will change with time, and it will decrease because of spontaneous absorption. So we're losing atoms going from level 1 going up into level 2 because the light has been absorbed. We've got a plus sign because we have atoms which are coming down from level 2 into level 1, increasing its number, and that's because of stimulated emission. And we also have a plus number here for the spontaneous emission, and certain atoms will stay up in level 2 for a certain amount of time and then fall back down again. So the 3 of these processes are absorption, our stimulated emission and our spontaneous emission. Those are the three basic processes that happen inside the laser. We've simplified things, we've made it so that there are only two energy levels, but it gives us a good idea to what's going on inside the laser at a kind of fundamental level. In thermal equilibrium, so if we turn the laser on and we let everything settle down, then in thermal equilibrium, the total number of atoms going up and the total number of atoms will be zero. In other words, we have a steady state will be zero, and so the left hand side here will be zero, and we can then establish a relationship between the spontaneous emission, stimulated emission, and the absorption. We can also look at the relationship that we already have between N2 and N1. We have Boltzmann's equation that the relationship between N2 and N1 is given by an exponential. And we can substitute those values for N1 and N2 into the expression in equation 14. So we can make that substitution and rearrange the equation to find the energy density or the radiation density. What we're looking for is the radiation density to increase. If the radiation density is decreasing, then mostly absorption, not getting emission. So we can rearrange that equation, equation 14, and give us something which looks like this, and we can compare it to what we had for the thermal process. So we have an exponential minus 1 on the bottom, we have an exponential minus 1 here, but we have a multiplier which is B12 over B21. So if these are predicting the same thing, these are predicting the shape of that curve, the black body radiation curve, they're predicting the same thing. And so they must be equivalents here. And that means that B12 over B21 must be equal to whatever multiplies the exponential in this case, which is 1. So that is 1 times exponential minus 1. And so this must be the same as B12 over B21. Okay. We can also compare the constants at the front, and I should add here that this condition is true because we have non-degenerate energy levels. If they are degenerate, then we have to factor in our values for G1 and G2 to give the relationship between B12 and B21, because it might be easier to get into level 2 than it is to get into energy level 1. For the constants, then we can see that comparing the two equations, we have that the ratio of A21 over B21 is given by this whole collection of stuff. Depends on frequency and the energy of the photon. That's why I've put the H21, nu21 separately here and the nu21 squared. So we can establish a relationship between A and B coefficients, and we end up where the B coefficient and the A coefficient are related to the wavelength to the power of 3 and the refractive index to the power of 3, where we've used the relationship that the speed of light in the material is equal to the speed of light divided by the refractive index. Or from equation 2, that this equation is valid. So these are known as the Einstein relations, and the most important thing to take away from this is that the stimulated emission is completely indistinguishable from the inducing radiation field. There's no way you can tell which was the input or the original photon and which is the copy, if you like, of the photon, because you have one in and then two out. They have the same properties across the board. They have the same direction. the same polarization, the same phase, the same wavelength and frequency. In other words, they are coherent. They are coherent with each other.